A hybrid car has an electric motor and a gasoline engine, so how is hybrids related to valence bond theory? We looked at the structure and shape of methane earlier. We also know from Chem 1A that a covalent bond forms when one unpaired electron from one atom combines with one unpaired electron from another atom. We also learned that a bond forms when atomic orbitals overlap to form that bond. So how do four bonds form the carbon, and why is carbon tetrahedral? We will use valence bond theory to explain why carbon has four bonds to it and why it has various shapes. In valence bond theory, two orbitals of the same atom combine together to form hybrid orbitals. A hybrid orbital forms when one s orbital combines with a p orbital from the same carbon. So here's the ground state electric configuration of carbon. Note that there's two unpaired electrons. This suggests there should be two bonds to carbon. However, there's four. So in valence bond theory, an s orbital combines with a p orbital to form two sp orbitals. These sp hybrid orbitals have the same energy, and look at the direction they're pointing. In this picture, an s orbital combines with two p orbitals to form three sp2 hybrid orbitals. Note the direction the sp2 hybrid orbitals point. In this picture, one s orbital combines with three p orbitals to form four sp3 hybrid orbitals. So stop the video and draw the orbital diagram that shows how these four sp3 hybrid orbitals form. So here's the answer. So here's the ground state of carbon. That ground state absorbs energy to form an excited state. Then the s orbital combines with three p orbitals to form the sp3 hybrid orbitals. Note the direction the sp3 hybrid orbitals point. It points to the corners of a tetrahedron. When hybrid orbitals form, they point in a specific direction. When a hybrid orbital overlaps with an orbital from another atom, a sigma bond forms. So let's use valence bond theory to explain bonding and shape. In ethane, C2H6, there's four single bonds to each carbon. From VSEPR theory, that means the shape at each carbon is tetrahedral. The tetrahedral shape tells us there's sp3 hybrid orbitals on each carbon. So stop the video and answer this question. The C1C2 sigma bond forms between which orbitals in each carbon? And the answer is F. What about the carbon-hydrogen bond? So stop the video and answer that question. So the answer is sp3 hybrid orbital on carbon and the s orbital on hydrogen. Let's take a look at the bonding in ethylene, C2H4. The structure tells us that on each carbon there's two carbon-hydrogen single bonds and one carbon-carbon double bond. VSEPR theory tells us that each carbon has a trigonal planar shape. The trigonal planar shape tells us that there's sp2 hybrid orbitals on each carbon. So stop the video and fill in the blanks in these questions. So here are the answers. Sigma bonds form between hybrid orbitals, but pi bonds form between p orbitals only. So let's put it all together. Let's relate geometry or shape to valence bond hybridization to the bond types. So for a tetrahedral geometry, the answers are: when carbon has a trigonal planar shape, the answers are. And for a linear shape, the answers are. Remember that hybrid orbitals form sigma bonds and p orbitals will form the pi bonds. Also note the different %s character and %p character for the different hybrid orbitals. Structure, shape, and hybridization also tells us about bond strength and reactivity. So stop the video, draw the structure of ethane, ethylene, and acetylene, and answer these questions. So ethane has a carbon-carbon single bond, ethylene a carbon-carbon double bond, and acetylene has a carbon-carbon triple bond. The strongest carbon-carbon bond is the carbon-carbon triple bond in acetylene. The valence bond theory reason is that the sp hybrid orbitals in acetylene have the greatest overlap, therefore the strongest bond. So the greater the %s character, the stronger the bond, because more overlap. The CH bond, which is the strongest, is the CH bond in acetylene. The sp hybrid orbital in carbon overlaps with the s orbital in hydrogen, and that has the greatest overlap because of the 50% s character in that sp hybrid orbital. An IR spectrum is the experimental evidence that shows that that CH bond is the strongest. Let's review, so stop the video and answer the first two questions. The answers are: a stronger bond has more S character, and a weak bond is more reactive than a strong bond. Note that a carbon-carbon single bond is unreactive, but the pi bond in a carbon-carbon double bond or triple bond is reactive. We will use these ideas later when we predict how organic compounds react to form products.